Hi, this is the first recorded lecture for MAS 4301. We're going to address some of the topics in Chapter 1, picking up with Section 1.4, I believe, and going through to the end of the chapter. It's a bit of a hodgepodge because it's just assorted topics that we'll need for later in the book, but hopefully you'll be able to follow with me as we go through it. Okay, so we're starting off with A of S. So if we let S be a set, then A of S is the set of F, or rather, let's just write it as bijections F from S to S. And recall that the bijection is a one-to-one and onto map. Okay? So that's A of S. In the special case that S is a finite set, so if S is finite, and we'll call its cardinality n, then A of S is denoted by Sn. It doesn't have to do with the name of the set, it's just the standard notation for the permutation group on n letters. Okay. Let's look now at some properties of A of S. First of all, we want to show that this is closed under composition. So if we have two bijections, Fg, in A of S, then we want to show that Fg is also in A of S. And let's bring that up here. Well, we would need to show that Fg is one-to-one and onto. So the way we would start is first we would show that Fg of x equals Fg of y. This implies, we want to show that this implies that x equals y. That would show that this is one-to-one. Well, we know that f is one-to-one. And that implies that if f of g of x equals f of g of y, then that means that g of x is equal to g of y. But we also know that g is one-to-one. And that means that if g of x is equal to g of y, that means that x is equal to y. So that finishes the job for us. And we can show that it's onto because if we take any x in S, we want to show that so for any x in S, there exists a y in S such that Fg of y equals x. Okay, that would give us that this is a surjection, or onto. And this is not so difficult. We know that how would we do this? We know that f is onto. So f is onto, and that means that there is going to exist a z such that f of z equals x, and we know that g of onto is onto, which means that there is a y such that g of y equals z, and that gives us what we need, because then f of g of y equals x. Okay, so that tells us this is closed under composition. I'm going to shift everything up a bit. good. Next property, composition is associative. So if we have 3 maps here, then, and these are all bijections in A of S, we want to show that f of g of h is equal to fg of h. Okay, and this is, it's almost kind of obvious just by looking at it. If you take an element x and then you apply h to it, and then you apply g to it, and then you apply f to it, it doesn't really matter where you stop. Like, I can stop here so that I'm doing only the h first and then go here, do the g and f together. Or I could stop, here, do the h and g first together and then do the f, but it'll end up in the same place either way. So it's a pretty straightforward property. The two-sided identity mapping exists. So basically, this is just I maps every element to itself. Okay, and if you have, a map F in A of S, then if I do F and then I do I, or if I do I and then I do F, and the maps that are on the right are the maps that end up happening first because they're closest to the element which goes in on the right. So whether you're doing I first, you just map X to itself and then do F, or you do F first, you map X to F of X and then you map that to itself. Either way, it's just the same as only doing F. So this is the two-sided identity. Give you a second to see that. And then two-sided inverses also exist. And here, so for any f in A of S, there exists g in A of S such that fg equals gf equals I, the identity mapping. And this is also relatively straightforward. Whatever f maps, just turn the arrows around, basically. So if you have, let's say you have the elements 1, 2, 3, 4 in your set, and f does this mapping. Then all I really have to do to get the inverse is just turn the arrows around. So and pretty obviously, if you do this and then you do that, you'll get back to where you start. And then the same if you do this first. And so let's say this is F, this is G. If you do this first, then you do that, you'll also just get back to where you started. So that's why these are inverse maps. Okay, now we have a comment about the cardinality of A of S. If the size of S equals n, so this is a finite set, then A of S, this should have cardinality, equals n factorial. And you'll recall that n factorial is the product of numbers n, of integers n, n minus 1, n minus 2, etc., down to 3, 2, 1. And the reason this is the case is that, given a set of n elements, it has to be 1 to 1. So you take your first element, you have n choices of where that gets mapped to. But then, so let's say our set is a1 through an. So f of a1, when you're defining what your f is, there are n choices. f of a2, because we can't have two things mapping to the same thing, since it's 1 to 1, you only have n minus 1 choices. And that continues. And when you have independent choices to make, you just multiply those numbers together to get the total choices. Okay, let's do an explicit example of what one of these A of S's looks like. So let's take S3. So S3, this is the set of bijections on set of 3 elements. We'll call them 1, 2, and 3. So it's always very simple. Just send everything to itself. That's the identity mapping. And we know that that has to be one of our maps. Oh, and we know that, by the way, that S3 equals 6. The size of S3 equals 6 because 6 is 3 factorial. So this is one mapping. This will be I. Then one simple thing to do would be to switch 2 elements. And we'll do that in the simplest way possible. Just 1 and 2, and then we can just cycle through them. So we'll switch 2 and 3 next. Then we can do 1 and 3. Okay. So in each of those, one of the elements was mapped to itself. And now we can look at the permutations, the mappings where nothing gets mapped to itself. So we can map 1. So we're saying it doesn't get mapped to itself. So it can either go to 2 or 3. So let's say it goes to 2. We know that 2 can't get mapped to itself. And it also can't get mapped to 1 because then 3 would be mapped to itself. So 2 has to be mapped to 3, and then 3 has to be mapped to 1. Okay, so that was one choice. The other choice we could have made would be to map 1 to 3. Okay, then we know, again, 3 can't be mapped to 1 because then 2 would be left to map to 2. So 3 has to map to 2, and 2 has to map to 1. Okay. Awesome. So these are the 6 mappings from the set 1, 2, 3 to itself. Okay, and that's our discussion of the set of bijections from a set to itself. And now we'll move on to some discussion of arithmetic. So we start with n. This fancy n is the set of positive integers, also called the counting numbers or the natural numbers. And that's why it's called n, because natural. If you want to add in 0, sometimes people write n0, sometimes people write z greater than or equal to 0. And that's just equal to 0, 1, 2, 3, 4, etc. Same deal, just add 0 in. These can be called the non-negative integers. As for z, this includes negative integers. So we have 0, -1, -2, etc. going off to the left, and 0, 1, 2, etc. going off to the right. These are the integers. I'm pretty sure the z comes from the German. I don't remember what the German word is right now, but that's easily checked in Wikipedia. Okay, so one great thing about the integers, or the natural numbers in particular, is that if you have two integers m and n, with n greater than 0, then there exists integers q and r such that r is between 0 and n, and m equals qn plus r. And this is just the standard division algorithm, if you have 27 and 4, okay, and I want, let's say m is 27 and n is 4. I want to find q and r so that r is at most, oh, sorry, this should be a strictly less than. R is less than 4 and greater than or equal to 0, and m equals qn plus r. So you just do standard division. So this goes in 6 times. So that's 24, and we have a remainder of 3. So 27 equals 6 times 4 plus 3. And this is an algorithm which is proven to work. Yeah, basically you can always just subtract copies of n from m until the next one you subtract is going to bring you into negative numbers. And at that point, you've got your remainder. Right, so how would I write this? So m minus n equals basically as an algorithm, to prove that this algorithm terminates, you take m minus n. If this is greater than or equal to 0, then you add 1 to q. Q equals q plus 1, and then you continue. You repeat. Okay, you keep subtracting copies of n until it's not greater than or equal to 0, and then what you're left with is the remainder. Okay, now we can talk about divisibility. So given integers m and n, we say m divides n if there is an integer k such that n equals km. Okay? So, in particular, 2 divides 14, 0 divides anything. I'm just kidding. 0 doesn't divide anything. Anything divides 0. 1 divides anything. And what else would be useful to have? If, for instance, you have a divides b, let's put this over here, a divides b, then you know for sure a divides bc. Why is this? Well, if b equals a times k, then bc equals a times kc, right? b equals ak. Just multiply both sides. bc equals a times kc. So that explains why this holds. Okay, and there's plenty of fun activities to be done on divisibility. Greatest common divisor, if you have two integers a and b, there is a largest number c such that c divides a and c divides b. Okay. So for instance, you know, 1 if you want to take 25 and 10, okay, their greatest common divisor, which is sometimes just denoted using these parentheses, would be 5, because that's the largest integer. I should specify that, largest integer, which divides both of them. Okay, another important theorem about this is that the GCD, greatest common divisor, also denoted just AB, is the smallest positive number written, and this should be positive integers probably, written as smallest positive number C, such that there are integers m and n, and these are not necessarily positive, with ma plus nb equals c. Okay? And there's you can kind of repeatedly apply the Euclidean algorithm to get at what that greatest common divisor is. So if we take 126 and 154, we're going to repeatedly apply the Euclidean algorithm for division. So we take 1 times 126, because that's how many times 126 goes into 154. And what's left over is 28. And now we take 126 and 28. That goes in not 5 times, but 4 times. 4 times gives me 80 plus 32, which is 112, which leaves over 14. And 28 equals 2 times 14. So indeed, what this tells us is that 14 divides both 126 and 154, and it's the greatest common divisor, the fact that we have 0 here. Okay. Equals 14. And if we wanted, we could work back from this to find a set of integers that gives us you know, 126 times m plus 154 times n equals 14. Let's see if we can do that. So we know that 2 times 14 equals, rather, let's put it this way. 14 equals 126 minus 4 times 28. And that's what we get from this equation. And now we get a new expression for 28 in terms of 154 and 126 from there. So we have 14 equals 126 minus 4 times 154 minus 126. And that tells us that 14 equals, so 126 plus 4 times 126 is 5 times 126 minus 4 times 154. Okay? And this is the smallest positive integer that you can get as an integer combination of these two guys. Okay. Just a quick note that things can be factored into primes. So you'll recall, of course, that prime number is an integer, a positive integer, greater than 1, whose only divisors are itself and 1. Okay? And what this theorem says, every integer greater than 1 can be factored as a product of primes, is that, take any integer n, and this is a product of pi to the ai. So take I to be in some index set. You're taking products of primes raised to powers. And the way that you can see this is true is suppose that there are some integers which can't be expressed as products of primes. Then you would be able to take the smallest such integer, right? So then take m smallest. But, okay, there are two possibilities. Either m is prime itself, but then that doesn't satisfy what our assumption is, that there's no such integer. So that means that m must be able to be factored. So m equals ab for ab integers. But then, because m is the smallest integer satisfying this property, that it's not the product of primes, both a and b are products of primes. Both factorizable. And I'm going to resize things. Both factorizable as a product of primes. And so you just multiply those two together, and that gives you an expression for m as a product of primes, which tells us that it never had this property to begin with. So that's a contradiction. Okay. Principle of mathematical induction. This is classic. The idea here is to say, let's say we want to prove that every natural number has a property. So for all n, p of n, the way we prove it, so the method of proof using principle of mathematical induction, is to say p of 1, let's say. You might want to start at a different integer depending on the specific scenario. So first you prove p of 1, and then you prove p of n implies p of n plus 1. Okay, and it's like dominoes falling down. The fact that p of 1 is true implies p of 2 is true, which implies p of 3 is true, which implies p of n is true for any n. And there are a number of good examples in the book to explore this. But this is a method of proof you should be familiar with. Okay, and the final section in this chapter talks about complex numbers. Every complex number can be written in the form z equals a plus bi, where a and b are real numbers. We haven't discussed real numbers, but it's not really in the purview of this class. There are various constructions of the real numbers, none of which are algebraic. And then I is the square root of -1. Okay, so you basically carry out, you can carry out arithmetic with these complex numbers as usual. Just whenever you see an I squared, you replace it with -1. So for instance, a plus bi, if you want to add them together, c plus di. This is equal to a plus c plus b plus di. That's fine. We know how to add real numbers together, so that's well defined as how we add. Okay, subtraction is same deal. A plus bi minus c plus di. Group the terms, a minus c plus b minus di. If we want to multiply here we're going to get some squared i's, so we have to be a little careful. A plus bi, c plus di. Okay, we have ac plus bci plus adi plus bdi squared. So we want to group this into the the things with an I and things without an I. So we have AC minus BD, because the I squared gets replaced by -1, plus AD plus BCI. Okay, so that's how you multiply complex numbers. Dividing complex numbers takes a bit more creativity. So if you have A plus BI over C plus DI, what you can do here is you can multiply top and bottom by what's called the complex conjugate. So you have C minus DI, C minus DI. When you multiply C plus DI by C minus DI, because cross terms cancel, what you're left with is C squared plus D squared. So this is going to be A plus BI times C minus DI over C squared plus D squared. And at this point, since this is a real number, then you can just distribute the real number to the real and imaginary parts here. The imaginary part is the part that has I. So we get AC plus BD. That's our I. That's our real part. Maybe I'll put this on the next line. AC plus BD divided by C squared plus D squared plus, and then the imaginary part, we have BC minus AD over C squared plus D squared I, and that gives us our division. So all of the arithmetic that we're used to, we can still handle even in this complex number system. Okay. We saw at the end there the complex conjugate. So if we have A plus BI, the complex conjugate is denoted by this bar, and it's equal to A minus BI. Okay, and it has the nice property that if you take A plus BI times its conjugate, you get A squared plus B squared, right? Just by cancellation of the cross terms. And this is really nice because what it tells us, if you have A plus BI, so let's say this is A, this is B, you're graphing A plus BI here. A minus BI is what you get, the conjugate is what you get when you reflect across the real axis. So this would be Z bar if our original number is Z. And Z times Z bar is the square of this radius, right? So this is the square root of Z times Z bar. Okay. And that's also what we call the absolute value of a complex number. Written this way, sometimes this way, usually this way. So Z equals the square root of Z times Z bar, or if we're in these coordinates, it's going to be equal to the square root of A squared plus B squared. And it's thinking about, thinking about this in terms of this complex plane, it's that radius, A plus BI. And that's why it works also for real numbers, right? If I plug in a or minus a, I get a in both cases because it's just the radius from the origin. Okay, polar form for a complex number, if you have z equals a plus bi. So we can take that radius we just described as r equals square root of a squared plus b squared. And then we're going to use a new notation in terms of an exponential. E to the I theta is given as cosine theta plus I sine theta. And this would take more time than we have here to explain, but rest assured it's mathematically consistent. So what if we start with a number z equals a plus bi, we plot that in the plane. So this is a plus bi. And then we look at this angle. So this is our theta. And then we note that a is equal to, so if this is r, then this is r cosine theta. And this is, sorry, that's r sine theta, my mistake. R sine theta. And this is r cosine theta. And that gives us a new way to describe this. We have a equals r cosine theta and b equals r sine theta. So theta really is the arctangent. So if we want to solve for theta, we can take dividing b over a, we get tangent of theta equals b over a. So it's like the arctangent of b over a. But once you find your r and your theta, you could write this as z equals r e to the I theta. Okay? And maybe we should do a quick example of this. So if we have, let's do z equals 1 plus I times the square root of 3. Okay? Then to get r, pretty simple, is square root of 1 squared plus the square root of 3 squared. Okay, and that's equal to square root of 4, which is 2. Okay, and then theta is equal to the arctangent of square root of 3 over 1. And that's equal to, I'm pretty sure, pi over 3. And so we could rewrite this as z is also equal to 2 times e to the pi I over 3. Okay? And if we wanted to graph this, we would just note. So we have 1 plus I root 3. And then we would just say this is 2, and then this is pi over 3. Okay. And we'll finish up with de Moivre's theorem, which says that if you have z equals r e to the I theta, then z to the n equals r to the n e to the I n theta. And using what we found before, this is r to the n times cosine n theta plus I sine n theta. So this gives us a way to compute powers of complex numbers very quickly, and for that matter, roots of complex numbers. So, you know, one thing you could do here, for instance, if I wanted to compute the square root of I, this would be equal to r e to the I theta would then be e to the pi I over 2, okay, because the radius of I is just 1. And then we're raising that to the 1/2. Okay, so the radius, since it's 1, just stays 1 to the 1/2. Nothing about that changes. But then we have cosine of putting the angle inside, we have pi I over 4, so this is going to be pi over 4 plus I sine pi over 4. Okay, if you remember your trigonometry, that's cosine of pi over 4 and sine pi over 4 are both 1 over the square root of 2 or root 2 over 2. I prefer 1 over the square root of 2. So this will just be 1 plus I over the square root of 2. And that's the square root of I. And that's that. That takes you through the chapter. Hopefully that helps you work your way through the lecture quiz as well. And I look forward to seeing you in next class.